Welcome to this lab module. Here today we will be discussing something like PVD, like physical vapor deposition, and we will be demonstrating the part. So till now whatever we have learned is, first we have shown do the gowning procedure, or what is the gowning procedure, what is the importance of gowning procedure, and introduction to the clean room. Then and we have a tour, and then in the next module we have shown how the cleaning was performed. So here we have shown piranha cleaning of a silicon wafer, 3-inch silicon wafer, but the same process can be done for the silicon wafer as well as for the glass wafers. In the next module we have seen how we can spin coat polyimide and how to make a polyimide layer. So that much was like film preparation. After that, one of the main part of that fabrication came into picture, that is lithography. So in our last module we have discussed what is lithography, how to do this, and different types of photo masks, different type of photoresist, and using positive photoresist, how we did that photolithography process. That much was described in the last till the last module. In this module, as we have mentioned earlier, we will see how to deposit titanium and platinum using electron beam evaporation technique, and then we will go for a lift off to get the metal patterning of the metal layer. So here whatever system you can see, this is one electron beam evaporation system. However, this system has capability of doing E-beam evaporation as well as thermal evaporation. In this module we will be discussing only about the tool first, what are the different parts of the tool and what is importance of these parts, and how to and we will demonstrate electron beam evaporation technique, and in some other module we will show how to go for thermal evaporation technique, and then in that module we will discuss what are the differences of the processes, and then if time permits we will show you another technique, another PVD technique, that is sputtering. So we will show all these all these processes in subsequent modules, but for today we will focus only on E-beam evaporation. So this is the chamber of this tool. So in this chamber, whenever we will open the chamber, we will see that in front side there is electron beam evaporation setup, and the back side is a thermal evaporation setup. So if let's say when deposition is going on, that time the chamber will be under vacuum, so we are not allowed to open the chamber. At that time we can just open this viewport and see whatever is going on inside. Now tool is off and there is no like light source inside, like when we do electron beam evaporation or deposition, that time we have one filament, that filament generates light, so that time we can see what is going on inside. Or even in thermal evaporation system, that filament or the due to Joule heating, that will also generate some light, so we can see what is going on inside. But now tool is off, so we cannot see, but this is the viewport, just so that we can observe the things inside. So here you can see there are two pipes coming. So these are water pipes, these are connected to the chiller. So here one of these is to supply the cold water or the chilled water, and the temperature will be around 19 to 21 degrees C. So when and it will flow in the inside as well as outside. Here we will show that later on. So here inside, outside, everywhere the connection is there, so it will be used as a coolant. So whatever temperature or the heat generated inside will be dispersed, and using the other one we will just maintain a flow of water, so that we can cool down the tools inside as well as the chamber. Now next let us see the other parts like inlets and outlets to the chamber. So this is that other side that we are talking about. So here are the pipes, and here are the lines what you can see, like for water cooling of the chiller. So here let us come to the inlet. So here the first one you can see, this is air supply. So this is a connection from the compressor unit. So as you know that few of the valves are pneumatic valves. So just to switch on or off or for the operation we need air supply. or some particular pressure, that will be showing inside what is the condition. This is a vent valve. So venting means putting air or inletting air in the chamber. So here this is the vent valve. You can see that just pipe is there and it is cut here. So venting can be either in clean room environment, or it is actually recommended to vent it using nitrogen. As we have enough purity of air inside, like purity in sense less number of dust particles here inside, so we are venting it in clean room environment only. Otherwise it is recommended to use nitrogen cylinder. Here this is needle valve inlet. So needle valve is used when you want any other gas to be inside, like maybe argon, maybe nitrogen, or maybe oxygen for your deposition. So if you want that type of environment in your chamber, then you can use this. And here you can see the cooling water in and out, as we have already shown there outside the chamber. This is the thing. And here you can see that this is rotary pump exhaust. So it will be shown here that there are two types of pumps available. So in any deposition system, the first one is used for taking the pressure from atmospheric pressure to some 10 to the power minus 4 millibar pressure, or 10 to the minus 3 or minus 4 millibar pressure. So rotary pump does that job. And there is high vacuum pumps, like it may be a diffusion pump or it may be turbomolecular pump. Those will be used for high vacuum, reaching the high vacuum. So this is rotary pump. So usually when rotary pump works, so that will have some exhaust. So that exhaust will be, can be like oil based exhaust or just the air outlet. So this, whatever the exhausts are there, we are taking it out and keeping it outside the clean room, or just throwing it outside clean room, because that may contaminate our clean room environment. So this is the things that are connected directly to the chamber. So now we will focus the other units as well. So after this you can see this. So this is for liquid, pouring liquid nitrogen. So let's say this is the chamber. So these pumps will take some time to create vacuum in this chamber. To make that process little faster, or not only little faster, but also to hold a particular vacuum level in the chamber, we can use liquid nitrogen. So as you already know that liquid nitrogen is having a temperature of more than minus 150. So that will help to get all the molecules here at the same place, so that it will be easier for the pump for suction. Okay, so here we can just pour liquid nitrogen. It will go inside. You can see the port from here. It will be inside there below this chamber, and as chamber is opened there, whatever molecules are there, that will go there and it will be stuck and suction eventually. So now let us come to this front side. We will just open this and see what are the components there inside that is making this whole system work. So here before opening, either you should make sure that power is off, or because here you can see already the things are written here that isolate main supply before removing this cover. This is connected to one of the safety interlocks. If this is on, then your tool can only create vacuum, but it will not go to the process step, or it cannot go to the deposition step. That is because of your safety reasons. And you can see here, this is electrical hazard sign. So now you know what you are expecting inside. If we open this, so here you can see the first one. This is a rotary pump that we were talking about. This rotary pump can create a vacuum up to 10 to the power minus 4 millibar range. So usually at atmospheric pressure, first this pump starts working, or this pump starts creating vacuum, and when the pressure reaches 10 to the power minus 3 or 10 to the power minus 3 millibar range, that time turbomolecular pump took over the things. So here, from here if you see, this is here how is the line is connected here, and here the next thing we can show is the roughing valve. So like that you have two valve here, roughing valve and backing valve. So these two are actually connecting the lines, because here you can see, so this is this one is common to both the lines, backing line as well as the roughing line. When it creates vacuum directly from the chamber, it works as the roughing line, and when turbomolecular pump took over the things, that time this acts as a backing valve. So it helps turbomolecular pump by creating a continuous pressure of -4 to the remaining area, and this turbomolecular pump will create vacuum in the chamber. So as we have shown these two valves, after that this one, as you can see, this is our turbomolecular pump. So it can rotate up to 13,000 rpm, and it can drag the particles or the air in the chamber to this, and through the line there, we cannot show it from here, through that line it will take the things out. Next, after these valves, we can see here the transformers. These transformers are, so at least this and this we can see, one more transformer is there for the E-beam. So these two transformers we can see, these are useful for thermal evaporation, so this we will discuss in the later modules. So now let us come to this side. So here you can see, so as you remember that from outside we are showing one air supply port there, or one air supply line, and that channel came through this, and from here we can see how much pressure is there and how much pressure will act on the pneumatic valves here, because that is one of the main thing that will decide whether the valves will open or close or will operate or not. So before starting the tool, if you are not sure, you can just check here whether you have the pressure, or if somehow the process fails, or if somehow the pump doesn't start working, you can just come and check whether this is on. And water cooling system is also there inside, and here this other shuttered things like whatever shuttered and all, we will show it inside. So those controllers are also inside, and backside there are water supplies. So here backside, as you can see, as focused there, so those are the supplies for DI water. This DI water will come through the chiller so that it can maintain a particular and preset temperature always for cooling the chamber as well as the electron beam gun. So we have seen what are all things we could show through this from this distance, and now we will come to this part. This is another transformer. So this transformer is used to generate electron beam. So only when we use this tool for electron beam, like generating electron beam for heating, that time we just switch it on, like just on, and we have one more supply that we will show later, while during the process we will show that. So here you have to on, and you can see here interlock and fan, these two are very important here, because as long as all the interlocks are not met, your system or this transformer output will not come, because this is 5 kilovolt system, or output is 5 kilovolt of this transformer. So it can give you one electrical shock hazard. So as this is very hazardous, this is, you cannot even take it out without opening the other parts, not like that. And the fan is required to cool down the area. So this is basic of this. Now after this, as we will switch on the tool in some time, and as we are done with that part, so we will close that door first so that the safety interlock will not be affected, then we will move to the other parts. Now we will close the door, and here you can see one interlock. So this one, when this will be closed, it will press this, and that will work as one of the interlocks to make sure that the door is closed and now the user is safe, and this tool can go to the process step. So we'll close it now. and lock. So after that part we will come to the controller part. So these are the units that will be controlled by this much of area basically, and this is the display. So let us start from the top. This is the display where the system status will be shown, and we can so this is basically touchpad based system. So this touchpad based display, so here we can select what are all operations we want this tool to perform. After this display, let us come to this part. So here this is you can see here 1 0, this is basically on off. So this is a press switch, like you can press it, it will be on, if you press it again it will be off. So this corresponds to main supply or the electrical supply of this tool. Here is the reset. So by any chance if you switch off the tool in hurry, or if you press this emergency stop button by because of some emergency, or if it is not on properly, there is some trip, some electrical issue, then there will be an hardware reset option. You can just reset it and then start the tool. And here if you see the next, these three are the indicators. These are not press switches, you can see here, we cannot press it. Basically these are indicators. The first one, as you can see, this is safety interlock. So safety interlock means whether the tool is safe for the user to go for the high power operations. Like as we have shown already that there is a 5 kilovolt transformer, so we cannot directly switch it on without covering the area, or without ensuring that we will not be in touch to that transformer. So like that, as we have shown one door here, front door, we have opened and showed you the things. So like that we have 3 doors to access the different areas. So all these 3 doors are connected to the same safety interlock, and with that the vacuum created in the chamber, that is also connected to the safety interlock. We should ensure that at least some amount of vacuum is there before starting the process. So all these things will be part of safety interlock, that when we will operate the tool, we will show the things again, like how vacuum affects it, how these opening doors will affect, all these things we will show. Though it is not recommended to leave the doors open and run the tool, because that will be electrical hazard for you. And here you can see this, the second one is the water cooling. Water cooling will be shown here, whether water cooling is on or not. This is that indication. So here, as already discussed, that chiller is required for cooling the gun as well as the chamber. So whether that chiller supply is on or not first, and second, whether the pressure created by the water or the water flow, basically whether the water flow is enough or not, that will be indicated by this. If it glows, that means it is we are good to go, or if it doesn't glow, then you have to go back and check whether chiller unit is on or not first, or two, somehow amount of water in the chiller unit is enough or not, or the third one, whether it is creating that pressure or not. These 3 things you have to check if this doesn't glow. And the third one is source enabled, as we are not using this tool in automated mode. So there are different types of tools, as you already know. So the tool can be completely manual, can be automated, and can be semi-automated type. This is a semi-automated type tool. If you see any automated tool, then their source enabled part will be there. So whenever deposition will go on, it will show. But in our case, we will just check this and this before starting the starting deposition. And here these two we will press. These are the buttons that we will press before starting the tools. And here one of the most important feature of any of the tools, that is emergency stop. So emergency stop button means you can just press it, and when it is done you can just rotate it. If you rotate, it will come up. If you press it, it will be off. It will off all the tools, all the valves and the parts. So here why I am telling this is very important, because if there is an emergency situation, like maybe for the tool maybe sudden power cut, or maybe there is some fire or some other hazard comes. So and maybe for some chemical hazard you have to leave the tool, chemical hazard imposed by someone else or happened because of some other tool, but you have to leave the place immediately, then you can just press the emergency stop and leave. So that is utility of this. So after this we will come to the next part, the controller parts. So this whole thing, this complete part, that is basically the controllers associated to E-beam evaporator or E-beam evaporation technique. Here the first one you can see, this is source control. In source control, so what are all you are expecting? So basically the first will be how much voltage you are supplying, how much current you are supplying, and how much current you are supplying, that should be controlled. And there are other parameters to check whether these are on or not, these are the indicators. Here let us discuss this thing first. So here this is the on off button, which corresponds to only this much area. So when your transformer is on, that time, like E-beam transformer is on, that 5 kilovolt transformer that we have shown, then you can just press it. This will be this is press button. After that you can wait for some time, start the gun. This gun corresponds to the electron beam gun. When the gun is on, after that you can increase the current from here or decrease the current. So basically you can control your current with this, and that indicator, this will show, this display will show what is your current level at that time. The value you can check from here. And this indicator, the first one, this power, this vacuum will show you, this power will show whether power is on or not. This vacuum will show whether enough vacuum is created in the chamber. Third one, water, will show you whether water supply is there or not for cooling the gun. Then the rotary drive, whether it is on or not. Then whether the gun is on. So this part will come only when you switch on this gun. And here local and remote. So local corresponds to whether the deposition is happening in manual mode, and remote will show whether the deposition is happening in automated mode. So as our tool is capable of only of manual mode deposition, so this local will be glowing. So these things we will just show during deposition as well. So here these are the other indicators that will show whether your tool is doing fine or not. With this HV adjustment you can actually adjust where the beam will fall. You can change it through that, and it is, once it is fixed or finalized, it is recommended not to touch that and shift the beam. So little bit beam steering can be done with this. So now let us come to the second part. So in the second part you can see this is basically sweep control. Sweep control means whatever beam we are generating, so now we will control the beam. So the beam may have maybe like a point, or maybe any of these waveforms like sine wave, triangular wave, square wave, and it will have two components like y component and x component. So that we can see here that x component controller is this part, y component controller is this part. So let's say this is x direction and this is y direction. Both can be controlled by these two controllers. Here as you can see, both frequency we have set it at 29 Hz, and here there is some offset like the HV adjustment. This also, once it is set, offset need not to be changed for all the depositions. Only what we are supposed to change is if we want it as a point source, then you can leave it as 0, so that this part will be off and it will generate a point source or point beam from the source, and it will fall on the crucible. And now if you keep it as 1, so now this panel will be on, and then you can select along y axis and along x axis and along y axis whether you want the waveform to be sine or triangular or square, that you have to decide. And here these two will be used to define the amplitude. If you increase the amplitude, then it will take more area, let's say, if you increase the amplitude, it will take more area. If you decrease the amplitude, then it will take lesser area on the crucible. That can be controlled by these two. Here, as in closer shot, you can probably see that for platinum, for titanium, like for different materials, we have already noted the things, but that optimization that you can do for, I mean, that is tool specific, and you can do it for your tool as well. Usually we deposit always at the sine mode, so like sinusoidal type. So along x-axis it will be like this sine, and along y-axis also it will be like this. So that will generate our whole, superposition of these two will generate the beam. Here, now coming to the third part. When we will open the tool, that time we will show again that we have 4 crucibles there. We will show that, and what all materials are loaded, that we will be discussing. So before that, we can just show that 4 are there, and this is the turret controller, where you can switch on this controller and you can change whichever crucible you want to select, and how fast that crucible change will happen, that you can select from this. So we always prefer to change the crucible at its maximum speed possible. And here, as you can see, like these are the indicators that you will see which crucible is selected. So we will come to this turret controller part later. Now come to let us go to one of the another important part, that is DTM. In this DTM, we can mainly see 2 things here, 2 displays here. One is about the rate, another one is about the thickness. And here, these are the parameters that defines one material for the QCM or the quartz crystal monitor. The quartz crystal monitor is inside, that we will show once we open the chamber. And here actually we can input properties of the materials. So we can select a film number, and correspond to that film number we can actually give the inputs as number, basically like tooling factor, then density, then ACI, or tooling factor again, tooling factor correction, like that. So with this we can just define one material for this particular DTM. So whenever we will go to that film number, let's say film number corresponds to titanium, or film 1 corresponds to platinum. So let's say when we will deposit platinum, as all these values are already there, so we will just select film 1, and we will get that stored values there, and from that we can whatever material will be deposited on the QCM or quartz crystal monitor, we can get a rate of deposition, and thickness means total how much thickness has been deposited. These two will get, and this is the controller, like start, stop and test, like that, for refreshing or for starting the thing. And increase and decrease, these two are useful to write or to give the input about film number and about these things. So this is this is how we are using this DTM or digital thickness monitor. So after DTM, this is the next panel. So here this corresponds to mainly current levels, then DTM on or off, DTM power supply, then shutters. So let us come one by one. So here this LT secondary current, HT primary current, and this these current controllers. These things will be discussed on the next day, because this corresponds more to thermal evaporation. So leave this part for this module. Let us focus on this part. So here, as you see, if we switch it on, then this is basically DTM will be on if tool is on, and here this is E-beam shutter. So electron beam gun shutter is here. So on crucible, on shutter is there, and it will be there as long as material is not completely ready for the deposition. So it will melt, and it will start, I mean, we have optimized the recipe. So as per the recipe, it will start at some point, it will be like, it will be ready for deposition in a steady rate. So till that time we have to wait. So after that we can just open the shutter. Here again 2 things are there, like local and remote. So remote corresponds to automated thing, that we don't have that option here available now. We have to put it for local and do it by ourselves, like opening it or closing it ourselves in manual mode. So this is controller of the shutter part. Here this is rotary drive controller. So if rotary drive is there, so if we want to deposit material in static mode, then we can just keep it off. If we switch it on, then rotation mode will be on, and after this rotation mode is on, that whole chuck that will be showing, that chuck, the whole chuck will be rotating. So if we there are differences that we will be discussing, but this is for rotation, and here rotation controller. So this will change the speed. Here for this tool we fix it at one point and we optimized all the recipes, so we do not prefer to change this or change this RPM. We just if we want stationary mode deposition, then we leave it here. If we want deposition in rotation mode, then we just switch it on. That you will have a better idea when you will see operation of the tools. So now we are going to switch on the tool. So as I have already mentioned, that chiller and compressor should be on. So that is here on my right side, that we will switch it on eventually, and then main power will be on. That connection, that supply is here. So let us come to this first. So here the first one is connected to the chiller and the second switch is for the compressor. So let's switch on the chiller and compressor. Then this is the kind of prerequisite for the tool, for operating the tool. Then we will go to the main power supply. So here I think you can see two switches, here one, here the other one. This, as it is already, we have written it for our purposes only, that this is the system power and this is electron beam gun power, EBG power, as you can see here. And here you can see this supply. Basically these two are different type of supplies. This is just like on 230 volt normal connection as we use, and this is to support a 5 kilovolt transformer. So this has some better arrangement for this, and one inbuilt ground line. You can see the copper strip here, this is going. So this is one copper strip that is going as earthing. This anyway we will switch on this only when we are about to deposit something, otherwise this should be off, just to avoid the electrical hazard. And this is the system power that we will be switching on now. After switching on the main power, so now we are here, as we have already discussed about this panel, so we have to turn on this power. As we have switched it on, you can see here it is asking for a reset, and with that it is showing that water cooling is already on. So as we have switched on the chiller, so it is showing the water cooling thing, but safety interlock it is not displaying because it asked for one reset button, reset, then only it can sense that. So let us go for a reset. As we press the reset, you can see the safety interlock is on, water cooling is on, and so we are good to go with the with our next process. So here you can see this is the display. See the status here, system status is showing standby. Standby means only I think if you can observe little closely, you can see that one fan sound is coming extra. So that is basically to cool down the tool. Whenever it is reset and other things are fine, then it will switch on the fans. So here you can see the system status as standby. Then chamber pressure. So any vacuum tool is supposed to be kept under some vacuum always, so that the chamber will be under some vacuum, let's say -4 level, minus whatever as you wish. Here as the Pirani gauge is showing, this much vacuum is still remaining in the chamber. We didn't use it for a long time, still it is like that. And here we have two options, like either start or vent. Start means it will start the pump, and vent means we can open the chamber, as we have to load our sample first, so we have to vent, open the chamber, and then we can go for the next steps. So let me press vent and then open the chamber and see what is there. Here you can see that after pressing vent, the system status changed to chamber vent sequence and air admit valve open, and you can see chamber pressure is falling now and it will reach atmospheric pressure. And if you closely if you observe, one extra air inlet sound you will get. So this is from the display, you can just check the things. Then let us wait for when it is showing that it is under atmospheric pressure. So we will try to open our chamber. As air inlet was on and now the chamber is under atmospheric pressure, so we are now allowed to open the chamber. So let us open. So here this is the chamber inside. I don't want to touch the things. Okay, so here this part is basically for electron beam evaporation. So here you may not be able to see here. Here is the filament. Okay, inside there is the filament. So that filament will be heated and electron beam will be generated and pass through this. So here we have one open area, like on square rectangular open slot. So from here the electron will come, will avoid this and fall here. So in the theory classes, I think you have already you have taught that one filament will generate the electron beam, and using the magnet here there will be a 270-degree deflection of the film and it will fall on the crucible. So you can see it here now. Actually through this and with magnetic film, magnetic field, it will come and fall here. Here you can see this is the shutter. So as long as this material is not properly melt or is not ready for evaporation, still some amount of material will come out. So this shutter will stop it and stop it from getting deposited on the chuck. So here is the chuck. We will show the chuck again when we load the sample. So, and here you can see two pipes. So basically these are the chiller, these pipes are from the chiller unit and to the chiller unit. One is inlet, the other one is outlet. This will be useful to cool down the filament and this whole module during deposition, and even after deposition you can just keep your chiller or you can keep your chiller on so that water will flow through this and it will be cooled down. Otherwise this is a filament made up of tungsten. The tungsten filament will be very hot and you should not open the chamber and let one hot filament to be exposed to the air. There is a fair chance that it will be oxidized or it will go bad also. So this is mainly about this module. This here you can see, this is a QCM or quartz crystal monitor. This is here it will be deposited at the front side. Here it will be deposited and the data we can get it from the DTM that we have already shown and discussed. It is there. And here you can see one turret. This is for movement of the turret or the crucibles. The crucible we will take it out and show before that. So this will be useful for moving the things. And here you can see right side, this facility is there to generate plasma inside for cleaning purpose. So we can generate plasma and clean the chamber inside. That is on. And back side you can see that is for thermal evaporation, that we will discuss in the next module or the upcoming modules in one of those. Here this is basically our chamber. Before that let us come closer to see the crucible. So to get access to these crucibles we have to open the shutter first. So let us remove the shutter, open the shutter. So here you can see one of the materials. As I already have mentioned that there are 4 crucibles. So let us just check what are all 4 crucibles there. So this one is, so here titanium is loaded, you can see. So how to take the crucibles out? It is like you can take any tweezer like that and just slowly take it out. Okay. And here you can see that these are basically the holders for the crucible. Okay. This whole thing, this turret can rotate or can move. So before checking the other things, I just want to press it. Okay, so before any deposition you should check whether enough material is there for the next deposition. That is something you should follow. You should not end up depositing your crucible material on your sample. That is something you should check. So this is the first one, titanium is loaded here. Then we already changed the things, so you can check here. See, it is rotating, moving to the next crucible. Okay. Here I guess from the color you can understand that this is gold. I'm just taking out this and show. Okay. So gold is loaded here. You have to just remember which crucible corresponds to which material, or what type of material is loaded in which crucible. That you have to just keep a note before deposition, so that you can you can deposit without without making any mistake. So here if you see this crucible, this is aluminium. So one quick note for who are not used to use these tools, so you can see some extra material here, right? So who are not familiar that much to this tool, just a quick note for them. You should not fill material more than 70% of any crucible, 70 to 80% max. If you fill more than that, it will spill. So when we started, this aluminum is like the cheapest material, and for any for testing purpose usually people use aluminum. So similar purpose we used aluminum, and it just got spilled a little bit. These type of problems may occur because of either shifting of the beam or not proper placement of the beam, or it may occur due to loading more amount of materials. So you should take care of this. This is aluminum, and as the next one we will show, you can see here this is platinum. So as already discussed the other day, that whatever patterns we have, we want titanium, platinum, basically platinum as the metal layer and titanium as the intermediate layer or the aeration layer. So we need to deposit this, and we have already shown that titanium is also there, and that amount of material what we want to deposit, that is also kind of okay. So we can now go for the deposition. That is our first thing. So as we will be depositing titanium first, so you should make sure that titanium will be there first, and then the gold titanium will be there first, and then we will change during the process. Okay, so this is how turret controller is used and how this can be used. And here if you can just see, it's rotating. You can check it from here. If some problem happens here, then definitely the rotation will be stopped. So as I was telling that it should be, in our case it is crucible 3 for our tool. We kept titanium in crucible 3. So let it reach crucible 3, then we will stop this rotation, or this will be stopped by itself basically. So see, now it stopped, and we have titanium there, and we have checked all the crucibles, and the materials are fine. So after all this, before starting the things, we will close this shutter, so that during heating up or pre-deposition heating, it should not start deposition directly on the wafer. Okay, so it's covered. So okay, now let us discuss few general things, and then we will show how to load the sample on that. Till now we have actually shown the crucibles inside, with loaded materials. So this is how the crucible look like. This is the spare crucibles. So here we can actually, if we want to load any new material, we cannot reuse any crucible. So we have to have some spare crucibles with us. Now crucible material can be different. like based on the material you are using it for, crucible materials are different. Let's say if material X will diffuse in material Y, then X and Y materials together you cannot use either as crucible material or the material to deposit. Then material X will diffuse through the material Y and you will end up wasting the material. So for using any, or for before loading any material, you should check whether the material diffuses through that, and you will find there are various online sources where you will find for a particular material, let's say for gold or let's say for platinum, what type of crucibles can be used. So that you have to check first, procure the crucibles according to that, and then you can load the materials and load it inside the chamber. Here two crucibles you can see here. So here the left hand, this is molybdenum based crucible, and right hand, this one is graphite based crucible. In close up obviously you can see the difference, like its smoothness, how it is made and all this. So materials and even weight, you can feel all this weight and you will understand the differences. Though from like a far look it may be of the similar color, but this is not the same material, you will understand these things. So here before loading any crucible, obviously you should just wash it, clean it once with solvents like acetone IP, and then you can put your put the material here and you can load it. So here if you see, this is of 15 cc. So like that, crucibles are available for different volume. So how much volume of material or how much material you want to place inside your chamber, that can be governed by what type of crucible or how much volume you are getting. These are 15 cc. So like that you can have 15 cc, 25 cc, 40 cc. These are like you can check any of the vendors sheet and you can understand what type of crucibles are available and what are the volume of the crucibles. So just a spare thing, I just showed it to you. And as you have already seen after one deposition how it looked like, so when deposition will be there or vacuum creation will be there, that time I will show you the materials as well, how the raw materials will look like. Okay, so now let us take this chuck out and we will show how to load the things, and we will prefer to load these things in a solvent bench, so we will go there and show you the things. So let us take it out. This is the chuck that we will be using. This is 12-inch chuck. 12-inch chuck means 12 chuck diameter is 12 inch. So like that, different diameters you can use as per, and different materials you can use, whether it is SS or it will be some other material that is of your choice when you procure it. Let us load. So here, as I kept here, you can see that after lithography, what the sample was, it is already here. It was in a desiccator overnight after post exposure bake and development, and after development we have performed hard bake for 3 minutes. After that, this is the sample, where actually last day we showed you the patterns as well. It was kind of visible that time. So we load this sample on this chuck and place it inside. So for loading the sample, there are multiple ways of loading the sample on the chuck. So you can see here the clamps. So if you have standard 4-inch wafer, then it is very easy to load using these clamps. And here we have 3 inches, though clamp can fit it, but we usually prefer using Kapton tapes. So you can see this is the Kapton tape. Basically this is a polyimide material. So the same polyimide material that is here, it is similar, but thickness will be different, and this is commercially available. So we prefer to use polyimide tapes or Kapton tapes. So so here if we see, so here we want to load it something like this. So here if we load it, here you can see top material is also polyimide, and here if we put some Kapton tape on this, and there is a sticky material, that is our gum, so it can peel the whole layer. So we have to fix this polyimide layer first on the back side, and based on that we have to load the things. So we'll take some time to load it. After that we'll come back again and show you how it is fixed on this. So here you can see we already pasted this sample using these Kapton tapes. Usually 2 or 3 like this will be enough, and we tried to avoid attaching tapes on the front surface so that this thing will not come out, or this polyimide film will not peel. That was our thing. These things are there. Now what is status of this sample? We can just recall the things again. So silicon wafer is is the supporting material. Then the substrate is this polyimide film that we have deposited, or we had prepared the film the other day. On top of it we have done lithography. So whatever patterns you are seeing, these are basically photoresist patterns. So there is no metal as of now. We are going now to deposit the metals. Let us load this in our chamber. So whenever you leave the tool or the chamber for some time, better you close it all the time, because the more time you will keep it open, it will accumulate more amount of contamination inside from this air only, and it will take more time to evacuate. So that's why I just closed the chamber and went there for loading. Here let us open the chamber. So this shaft is there to hold the chuck. We'll load it like this. This is fixed. Now this shaft can rotate, so that this whole thing, this chuck will be rotated. So here we will show you today first the stationary deposition, and then deposition in rotation in same vacuum level only. So first we will just let us just, as I told already, that I will be showing stationary. So for stationary deposition, always it should be exactly above that, so that deposition will be maximum. If it is in rotation, then you don't have to worry, because then whole chuck will be rotated, and in rotation always uniformity is better. So we prefer deposition in rotation always. So you have to remember that when you are optimizing any tool. But in other case, if you want some, or if you want to deposit some material like gold or platinum, some precious material, then you can prefer stationary mode depending on your sample size, and if there is only one wafer or something like that, and you don't want to waste material all over the chuck, only if you want to deposit here, then you can go for it. That is your choice. You have to optimize your recipe in that way, but we will deposit in rotation only. Okay, so here is the first thing, and as I have already mentioned about this hole, like rectangular hole, how this will come through that and it will be deposited. Here is the cover, here is that, and we have our substrate here. So now we are good to go, and you just check by mistake. You should not keep any loose object inside, like let's say like tweezer, let's say like one of the screws. You just check that, and as there is nothing, just let us close the chamber, and then we will go to the process. So let us close the chamber. This is done. Now here is our tool. So now let us see what is that tool condition. If you see here, safety interlock is off. As I already mentioned, that safety interlock corresponds to the doors, like whether all the doors are closed and whether there is some amount of vacuum there in the chamber. As it is under atmospheric pressure, so by default the safety interlock is off. Now I'd request to focus this area, like this and this, so that we will just show what is the status. So So as a closure loop, you can see that, see one more thing here, in most of the tools whatever is allowed, that will be either in glowing condition or this, or some color difference will be there, like what are all allowed things and what are all not allowed. So here similarly we can see that we can go for start or we can go for vent. Vent already we have tried. Vent is for venting the chamber and open the chamber. Now here is the start. So start, it will start the pumps basically, and so let us try that. Here you can see that chamber pressure by Piranni gauge measured by using Piranni is at atmospheric pressure. Let us start. As we pressed, see, so first it start the backing pump. So after this backing pump, let's see, and after this backing pump it will start turbomolecular pump, and then see after backing pump started, it started backing process. So backing process is there are two lines basically that you can see from here, system view and mimic diagram. So here you can see this is the rotary pump. This is acting as a backing pump now. How? See here there are two lines. One is roughing line, one is backing line. Backing line is through this. So here as you can see, this is our chamber. So through that we are taking the connection here. So backing valve is open as it is glowing, as I already told. A backing valve is open and roughing valve is closed. So through this line we are creating the vacuum now. Why backing line? Because before starting this turbomolecular pump, it want to make some sort of vacuum. Okay, so here is the reason. So this P1, P3, P2, these are the gauges. So P1 is the Piranni gauge, P2 is also another Piranni gauge, and this is P3 is Penning gauge. What is Piranni gauge and Penning gauge? These are already covered in theory session. We will discuss it again, but before that, so as you can see here, turbo pump is on, it is glowing. So let us go back to the system control and see what is the case. See, it is showing turbo acceleration. So as turbo pump was off, it was having some 0 RPM as a rotation. So here it will increase to 13,000 RPM or its rated speed. That will take some time. So this is the so that is why we are seeing system status as turbo acceleration. It will be turbo ready. So when turbo pump will be ready, we can go for vacuum cycles. So let us wait for some time as long as turbo acceleration is going on. So now as we can see, after waiting for some time, turbo pump ready. So now we have these many options, like stop, we can stop the tool. So stop means it will basically decelerate the turbo pump and it will prepare the tool shutdown step. Cycle is like vacuum cycle, we can vent at any moment till now, and process. So we can start deposition, but as we know that deposition is supposed to be at 10 power minus 6 millibar pressure or that much of vacuum, so we cannot go for process now. So we have to go for vacuum cycle, and vacuum cycle is automated here, that we will see here how it works. As turbo pump is ready, let us press cycle and then explain the things further. Cycle. So first it will start with cycle sequence roughing. So first roughing cycle will start, that we can see here. Let us go to that diagram. Okay, so here you can see now backing valve is off. So one second, yeah, now backing valve is off. So this backing line is completely detached. So this is not creating vacuum through this line. It is and see here roughing valve is on. So it is creating vacuum from this chamber to this line, and by this time you could probably notice that this safety interlock is on. So this requires at least 10 power 1 millibar pressure. So it should be two times, I mean almost like 100 times less than the environment pressure, like atmospheric pressure. Then only this environment is little safer for the user to go for deposition or other things. So that is ensured by this. Here you can see only P1 and P2 is active, so P2 is here. This is giving almost like P tiny gauge connected near to this line, and the other one is here in between roughing and backing line, almost nearby this roughing pump. These two are giving the values now. So you can see here some volt is coming, so that much voltage, that is that sensed voltage. So that voltage is converted to pressure, and from there we are getting this value, this some millibar. So here you can see safety interlock is on, this is also on, this is ready basically, and this is also on. And now let us go to system control, because we can do everything from there only. So we will be there now. So okay, here if you can see it is e power minus 1. We will wait till it goes to the high vacuum or high vacuum valve opens, and it goes for fine pumping through, or using turbomolecular pump through the backing line. Till that much we will wait, we will show in video. After that we will again come back when it will reach -6 pressure. So let us wait for that much time, like few minutes maybe, it will come. So here you can see it is going down, it's -2 now. So we will wait for some more time, it will start fine pumping. Till now it is pumping through the now it started through the backing line. We can show it. See, now this high vacuum valve, this is on, so it is through this backing line now, and this roughing line is closed. Okay, so and this P3, that the penning line is activated now. Now we will wait till we can see that fine pumping starts. Okay, but this will be the configuration for that next, let's say it will take 1 hour or 1.5 hours. So this will be the configuration for that, through this pumping through this line, and it is already reached -4. So go to system control and see -4 to the M gauge, and here you can see system status as fine pumping. This will continue till -6 range. Let it go there as it is, and let us come let us focus on little bit details about the gauges also. So gauges means there are usually two types of gauges that we are using for these vacuum tools. So one is P tiny gauge, another one is penning gauge. So P tiny gauge is something that is good for measuring higher pressures, like a higher pressure means from atmospheric pressure to e power -3 or e power -3 or e power -4 millibar, that much it can measure. And penning gauge is good for measuring from e power -2 to e power -6 or 7, also it can measure e power -7 millibar pressure. So as for this tool we will be we have this atmospheric pressure range, as well as when it will be under vacuum we need to measure e power -6 or e power -7 millibar range. So we have both the things. However, we cannot show you the P tiny gauges and penning gauges as of now, because then we have to actually open this whole thing. So we don't want to open the setup as of now. So here these are the two types of gauges. As you can see here, already M or the penning gauge took over the things, as it was -4 that time, and still this time it is -4 millibar range. So let us wait till it reaches e power -6 pressure, or actually we prefer 3 e power -6 pressure or 4 e power -6 pressure before starting our process.